signals, the transmission speed, or what are the pressure signals. All these things can be actually captured. And once captured, then signal analysis and signal conditioning can be done over there. So methodology, if I have to look at methodology, I look at three major objectives. The first objective would be to study the existing system to understand the signal levels, because I'm not sure what exactly is the sensor that is used right now in the lab, and what exactly is the signal level of this. So it is very important to understand this. And any pressure sensor that you take, then you need to have some signal conditioning to it. One thing that we need to give is, we need to give a power supply to the pressure sensor, and we have to also understand what is the current levels required for the pressure sensor to achieve the same output that is required. So the block diagram of what we want to build will be something like this, where we have a pressure sensor. The signal conditioner will be actually trying to give you the required inputs, and we'll have to develop an instrumentation based amplifier. And this amplifier will actually amplify the signals that is coming out of the pressure wave sensor, where your signal conditioner will also trigger this amplifier whenever it is required. So once this is over, then the next step would be to basically have the data acquisition system, which is actually coming out from your objective 2, where we'll use an analog to digital converter, high speed analog to digital converter, which actually converts in terms of megahertz. And then we'll have a high end processor. And right now, the one that I'm thinking of, the one that I'm proposing, is to be basically an ARM based processor with an IoT node, which will help you to at least do the minimum amount of processing, and then also have some kind of ways to send the entire data to a cloud. And then we'll have to have memory to actually keep this data first initially before sending it to cloud. Okay, so this entire three portion of the block diagrams will be part of an ARM based processor with an IoT node. So next comes objective 3, where we'll have to characterize the signals, send the output to a common cloud, and then later on we have to do analysis and trying to understand from the signals what exactly is the blast wave looking like. So current strengths from my side is, this project is something very new to me. I've not worked with defense related projects till now, but it is quite interesting. That's the reason I've applied for it. And actually, for the last 12 years, I've been working on development of biomedical instrumentation, where we work on development of photoacoustic instrumentation for the last 12 years. What we did is, the photoacoustic instrumentation is a biomedical technique which is used for cancer diagnosis. And usually the equipments that are available for photoacoustics are all huge equipments which cannot get into any clinical setting, and it requires a good amount of engineers to actually set up the entire system, then prepare the entire tissue for sampling, and then ultimately acquiring it. So what we did is, in order to take it to some clinical settings, we have some collaborations with hospitals. So in order to take it to clinical settings, we removed some of those parts, and we wanted to bring it everything into an electronic system. So in that one aspect of what our group built is to build a data acquisition system. We work in terms of 45 megahertz of sample collection, where we have a PCB which actually collects the. It's also a piezoelectric sensor, because it's acoustic, so it requires some sound. And those acquisition basically comes over here, and then we use a microcontroller to basically acquire the signals, do a real-time averaging of the signals, and do some kind of signal processing, and ultimately taking it to a computer for displaying the results. So this resulted in a couple of patents at this point of time, and the third patent is actually filed. So, so with this, I'll move on to this funding support. So right now, I'm thinking of having one manpower for a period of 2 years. So the timeline of my project, I'm thinking of doing 2 years. And some of the electronic consumables which we would require for doing this electronic data acquisition system is to look at some DSP boards, electronic single board computers, extra, etc. And for the signal conditioning, we may need to build a development of a low power control electronics. And I mean, depending upon the number of sensors that you want to try, I'm projecting it to have a, yeah. So I've kept some money for travel and overheads as per the institute norms. So with this, I'm ending my presentation. Thank you so much.
Thank you. Sir, sorry, sir, we are not able to see what is the final cost for approximate.
I'm aiming it to around 60 lakhs for a period of 2 years.
Okay. So, sir, your proposal is very good, but slightly we need some fine tuning.
Yes.
First thing is, what is the size? We have to check it. And second thing, in DRDO, it is not allowed to send the data on the any cloud service. So we have
Okay.
to think about the localized storage of the data.
No, if let's say you have a cloud server which belongs to your own DRDO, and then if let's say we,
No, no, sir.
that is also not allowed.
No, sir. In field, where sometimes we are conducting trials in the remote location, so it may not possible that internet will be there.
Okay.
So
Okay.
that is
Okay.
anything it is not allowed. So we have to think about the storage of the localized data,
Hmm. Hmm.
and then
No, in my
second,
photoacoustic instrumentation, whatever I have done so far, we have not done through cloud. We actually had a local memory to actually store every
that is
data and
okay,
then
sir.
communicate. So I think I can fine tune the system to that extent. Yeah.
So
Understood.
size and then local storage and then synchronization of the data system. These are the three main points, sir.
Okay. Okay.
And for our sensor, what we are using at present IEP based mostly sensors. So you
Okay.
can know companies are Kistler or PCV USA. So
Okay.
you can see.
PCB. Okay. Okay.
Yeah.
Okay. Sure.
So any
Yeah.
point from Rajman from your side also?
Yeah, I want to just add, Professor, that Wi-Fi and Bluetooth technologies basically they are actually not able to transmit the data at faster speed, and the distances which we are looking for they are around more than 100 to 200 meters
Okay.
in our experiments. Okay, so as suggested by Dr. Indrapal, that we should look for a localized storage, maybe around 5 meter or 10 meter away, using the conventional cables, and then we can basically combine that data through an optical link.
Okay.
Okay, we can
Okay.
lay one optical fiber line, and we can store at the server,
Okay.
transmit at the server that data.
Okay.
Okay,
Even if
so
it can be stored on the inside within the sensor also, that will be also important. With the individual
yeah,
sensor, we can put a small data system.
yeah, that has to be basically connected to always connected through optical fiber only. No?
Yeah, later
That
on we can connect.
yeah,
Okay.
yeah. And second point was that LoRa again it is related to Wi-Fi only. Okay,
Because I
telemedicine.
was planning to do it through Wi-Fi. That's the reason my presentation was towards Wi-Fi.
It is not feasible in our
Now I understood the point. Mm.
yeah, yeah,
Mm.
yeah.
I
So
understood.
that
So I'll try
so
to fine
second
tune the.
that if it is feasible, you can plan a visit to TBRL to Dr. Indrapal or to me, so that we can actually have a detailed discussion on this.
I'll be very happy to do it, sir.
Yeah, yeah. You may be given some data sets of also which have
Yes.
been acquired, and you will actually gain the real time experience that how we are doing now and what we are expecting from you.
Okay. Okay. That will be very good, sir. I'll be very happy
Thank
to
you,
visit.
sir. Thank you, sir,
Ah,
for nice
thank you, sir.
presentation.
Thank
Okay,
you, sir.
sir.
Thank you so
We
much.
will keep in touch, sir.
Sure, sir. Okay. Thank you so much.
So our next speaker is Mr. Suresh Kumar. So, sir, you are here. Please unmute.
Sir.
Go ahead with presentation. You are audible.
Yes, sir.
Yeah. So screen is also visible, sir.
Thank you. Good morning, sir. Very good morning to one and all person here. So the proposed idea is shock mitigation solution, and the second one is shock dissipation by providing grooves on casing. These two are the important problems we are planning to propose right now. So actually, since from the problem statement given, it's clear that the conjoint action of shock load as well as the fragmentation causes the explosion of the adjacent box. So this is what we understood from the given statement. So to overcome this, there are several solutions have already provided in the literature review, like rigid explosion proof structure, flexible explosion proof structures. So we plan to start with the flexible explosion proof structures by incorporating or enclosing the each explosive containers. And this is proposed to be initially to start with the numerical simulation only. So whatever the upcoming slides we are going to be, I'm planning to provide them numerical solution to the coated or covered explosive casing. So that is the main idea for this. So for the from the literature review, it's very clear that the blast several researchers have made attempt to address the blast behavior of the uh, explosive storage tankers by considering the either blast wave alone or fragmentation part alone. But in our solution, we are planning to provide a numerical solution by by joining the both shock wave as well as the fragmentation influence on the uh, target. So that is the main focus of this. So it can be done experimental focus right now, we not yet planned. So the numerically it can be achieved by using the numerical code abacus 2025 version along with the composite modeler also. So using this initially, whenever the explosion happens, first the shock wave generates, then followed by the fragmentation. If it is of a close proximity, before the shock wave reaches the target, fragmentation part attacks the targets. Similarly, as the time increases, the reverse case also happens. So how to model it using the numerical simulation is our main objective. And as so the whenever the explosive is kept inside the shell, or there are several types of explosive modeling also there in the experimentation part is concerned. But in reality, so the proposed solution, either axatic structure, say a honeycomb panel or a sandwich structure, is planned to be analyzed. So sandwich panels, but they both consist of a composites, both top and bottom, in along embedded with the axatic structure or any other honeycomb panel, or core filled structures, core filled foam core filled structures also we can plan. But it before going to the experimentation part, it needs to be analyzed. So that part we are interested in doing with the abacus numerical code. So the proposed solution will be the one which is shown in the images. So both the top and bottom is a composite panels, because the normal stress will be high at the closer to the surface level. When the shock wave transfers to the when the shock waves transmitted further, then it needs to be mitigated. So the structure, which is the embedded structure between the core plate, between the two top and bottom plates, will take care of that particular aspect. So this is planned to be done. That is, the initial data set or initial investigation will be done by using the abacus 2025 numerical code. So the shock wave, even the TNT of TNT will be modeled. That is, the explosive will be modeled either by using Gears Hunter model or JWL model or several material modelings are available for the explosive part. And then for the shock to travel through the air, because most the problem statement is deals with the air explosion only. So in this way, con-BEP model, that is explosion in the air category, can be considered to study the or investigate the influence of shock wave, that is conjoint shock wave, along with the fragmentation. The conjoint action of these two will be studied on the target. And the problem statement is given clearly mentioned that we need to develop a novel material or container which will protect the explosive container. So the explosives are already stored in the box. For example, the explosives are stored in the box. It needs to be protected, or it needs to be, or suppose if among the 9 box, if anyone gets exploded, it should be prevented in transmitting to the other cages as well. So using this new material, initially analysis will be done to understand its blast performance. So that is time versus peak force graph also will be plotted for the idea considered in the present investigation. So, and using this, since it's a numerical focused alone, we don't want the much more fund. More fund is required only when we go for the experimentation part. For the numerical simulation, your workstation and a software license for about 1 or 2 years is sufficient for us to model the explosive as well as for the target. And the unique important point is in the conjoint action of both the shock wave as well as the fragmentation part can be studied for the material which we considered. So already I am heading the NRB project for the underwater explosion, similarly underwater explosion of the naval grade steel plates. So these are the quickly I go through the work build which already presently I'm working with. So I'm working with the how to model the shocks, how to model the underwater shock test for the
Hello,
naval grade.
sir.
Yes, sir. Yes, sir.
Sir, sir, time is less. Please come to the second proposal.
Sure, sir. Sure, sir. Sure, sir. So this is the modeling of the target material properties required for the target plate, and then as well as for the explosive also has been modeled in this way. And then this is the initial solution. In the second problem is concerned. Yes, sir. The second one is, for example, by introducing the grooves, how the and the fragmentation shapes and other mechanisms can be changed. So for that, initially we are planning to go with the stiffened model. So this is the initial work which we carried out related to the present one. That is, a target can be modeled with the, for example, first one is the with the cutout, and second one is with the stiffened plate. So this is a cutout model, and second one is a stiffened plate. So in this way, for providing the grooves, we not yet attempted. So in this way, by introducing the several type of grooves in the surface of the casing or container, we are ready to, we can able to study the shock response of this for a various charge location and then charge distance. So the dynamic deformation behavior of the target, uh, because of the contact with the shock wave, can be studied. That is the major advantages of this. And this is a methodology which we can formulate to understand the shock behavior of the material. And then the finally, for example, the methodology starts with the material modeling is the first one, explosive modeling is the second one, and then the loading conditions, that is creating a contact interactions between the shock wave with the target, is the second one. So this is a second idea. That is second idea actually we confirms that to we are ready to provide the numerical solution to the shock behavior of the target by incorporating the grooves or stiffened plates or any structural modifications. How it will behave for the various charge location and distance is the first one. That part we can ensure in the second problem. And then the third one is ballistic impact of the impedance graded steel targets. So in this case also, steel with, that is, instead of a one single target, what will be the influence of the layered impedance grading? That is, for example, steel with the aluminum. So the weight reduction is the major concern for the problem 3 is concern. So already we are working with the impedance grade trip steels aluminum 7075 layered composite. So when the projectile hits the first layer, every wall will behave like obstacle or prevents the projectile's motion. So in this way, we are trying to propose a new target embedding the trip steel with the aluminum 7075 target. So that is the third idea related to the ballistics is concerned. So since right now, apart from the third idea, the first two ideas, we are planning to go ahead with the numerical simulation first. So based on the numerical simulation, if experimentation part is, if the numerical simulation needs to be justified, then we are ready to conduct a few experiments in this domain also. That's all, sir.
Hello, sir.
Yes, sir. Yes, sir.
Yeah.
What is the cost?
So what is the cost and duration for this proposal, sir?
So for the first one, sir, actually we are in initial stage. We are interested in doing the numerical simulation only, sir. Even for the
Yes,
first
yes.
one, for example, the shock mitigation techniques and all, we are interested in doing the numerical simulation. But even we don't want the perpetual license also. Software license for about 1 or 2 years. That is the project
Yeah.
duration is
For second proposal, sir. Sir, this is the for first proposal, and the second proposal, what is our duration and the approximate cost?
1 second, I'll go, sir. For the second one also, sir, it's a numerical. Second also numerical only, sir. And before,
Yes.
sorry, this is third one, sir. The second
It's
one,
3
1
years.
second.
I think your last slide showing 3 years.
45 lakh 3 years.
No, no, sir, that is for the ballistics part. Ballistics part. But for the stiffened panel, it is not that. Yes, sir. For the stiffened is 35 lakhs is sufficient, sir. Because even if I get the same software license for the project duration, that is 1 or 2 years for the software license, that is sufficient. And simple tests are required to determine the material's behavior at high strain rate. So very
Yes, sir.
simple experiments. For example, if you go with the composite stiffened panel, then the JC parameter, migration equation of state, JWL parameter. So these parameters needs to be determined before starting the numerical simulation. So for that, simple experiments are required at the initial stage, sir. Apart from that, only the software cost is the major one. Rest of the things, it's not a major concern, sir. Suppose if we want us to make a experimental validation for the numerical simulation, because right now we are working for the SPH algorithm, sir. SPAS algorithm we are using, smooth particle algorithm we are using for the bird heat impact for GTRE also. even the dynamic simulation that is also it's in the preliminary stage. So definitely we can do the shock simulation of the target for various configuration using the numerical parts, sir.
Hello, sir.
Yes, sir. Yes, sir. I'm audible, sir.
Yeah, sir, there is some glitches. So, okay, sir, we have understood that you have the good capability to do this simulation parts.
Okay, sir.
Only thing is that if you can add some experiment work also, that will be much better, so that we can verify that the results are good or
Sure,
matching
sir.
with our expectation.
Sure, sir.
So,
Sure, sir.
any point from Rajwant your side? Hello, Rajwant. Anyway, sir, thank you, sir. Thanks a lot for your participation. And
Thank you so much, sir. Thank you, sir.
okay, sir. Thank
Thank
you.
you, sir.
Hello, sir. Indra Sen, sir. Hello, Dr. Indra Singh.
Yes, sir. Good morning, sir.
Yeah, good morning, sir. Sir, you can present your work.
Yeah, so I'm now sharing my screen. So, is it visible? My slides are visible, sir?
Yes.
Okay. Okay. So this project is in collaboration with four of my colleagues in IIT Indore. So motivation is, we have storage. We have munitions stored in a particular place, and if any accident happens, so that that accident or enemy attack may trigger the blast of, blast of these warheads of these munitions. So in this proposal, we want to propose a development of uh, auxiliary structure which can resist blast and ballistic loading, and that structure can be used for uh, to design a casing for package boxes for these kind of overheads. So motivation is, in the recent past, sandwich structures comprised of cellular soft materials sandwiched between two stiffer plates has been proposed, and because they have shown excellent shock mitigation characteristic due to high specific strength and great specific energy of absorption. So this is the typical arrangement of auxiliary sandwich structure. In addition, people have shown that for high, in case project velocity of fragments are high, the people have suggested to use a Kevlar or some fiber composite in addition to these top face plates. So there are different material people have suggested, like for designing of core, foam, here cellular honeycomb and auxiliary honeycomb people have suggested. And many authors have suggested combining these two together and developing composite structure comprised of protective layers of FRP and the sandwich structure. So the this behavior of these, fragment blast and fragment mitigation capability of this structure is depends on many things. For example, material combination, stacking of different layers, shape, size, and cell in core and cell wall thickness. So for given loading condition, one has to optimize these numbers. And in literature, most of the time, people have reported using a combination of optimization algorithm along with this finite element simulation. So this is one typical algorithm taken from literature people have used, and we have also used this kind of algorithm in the past to optimize the material parameter for BCC single crystals. But these are quite fast, but still they takes time, because in these simulation people model discrete cells, these cells of honeycomb, and as a result, number of elements are very large. So this time involved in optimization can be further reduced if by using a homogenized model. And very little work has been done this in direction. So we want to take up this as one of the problem in this project. In the recent past, auxiliary structure had gained attention because of high negative Poisson's ratio. As a result, this shows lesser deflection in the back face seat and high energy absorption. Various design has been proposed in objective structure. For example, the conventional objective structure, and these are some advanced design. These are I have shown few cases here, but there are many which have been reported, and Poisson's ratio for those designs are much higher. But problem is this: to manufacture these objective structures not easy by using conventional manufacturing technique. That's why mostly people have used for FEM simulation. So in this table, I have summarized objective structures used and material used for their manufacturing, for the core, and material used for face plates, and type of loading they have studied, blast loading, impact loading, and how they have studied through experiment or through simulation. So first observation, we can see that mostly people have used aluminum alloy here, and few authors have used steel, and few authors have used titanium alloy also. And most important here, experiments are performed only in simple design which are reentrant type or arrowhead type, because these designs can be manufactured through conventional design. Other designs which are capable of showing high negative Poisson's ratio have been not tested through experiments. The reason is manufacturing challenge. So to overcome, now authors are trying to use additive manufacturing, and here I have summarized from literature. So these four material have been used: steel alloy, copper alloy, and aluminum alloy. And this is another steel alloy. By using additive manufacturing techniques, so these are typical size they have able to, cell wall thickness they could able to produce. So for the case of steel, they were able to produce minimum of cell wall thickness 0.16 mm. And however, is aluminum, which is mostly preferred for conventional manufacturing, they could able to produce up to 1 mm only. So now this is difference around 6 times here. So now this suggests that if you go for additive manufacturing, steel is still good idea, because one can fine tune. I mean, it offers more flexibility in tuning the design parameters here. Another advantage, the other important point we can see from this table, most of the study, they have done either blast loading or impact loading, right? And except this author, where they have done both loading together. But in this also, they have done only, first they have applied blast loading, one study, another study they have performed impact loading, and they tried to summarize based on the adding the solutions on these two. And but it's not right way, because in actual application, the structure will experience combined loading. So now these structure has to be tested. So there in literature, it has been suggested that by using fragment simulated projectile, one can experiment combined loading of fragment as well as shock loading. So here they use this kind of projectile. So this is foam projectile, and it has inside a fragment projectile. Both are, the fragment is free to move inside. So when this projectile is launched through gas gun setup, so this foam projectile hits target before this one, fragment, and it generates shock wave. Later, this fragment projectile goes and hit and generates a fragment loading. So this delta D, by tuning this delta D, one can simulate the arrival time of shock loading and fragment loading. And one author has shown that this combined effect, right, has significant role on the, ballistic resistance of some fiber composite. And this in literature, this kind of studies has not been reported yet in objective structure. So if you are developing a structure for shock and fragment loading, combined loading, so this has to be tested. So in this proposal, we want to propose a development of lab scale 150 mm by 150 anti-blast and anti-fragment objective structure made of steel or aluminum, because steel offers more flexibility. So based on the requirement, we choose this material. And in literature, till now, the maximum size of structure what people have reported through additive manufacturing is the 300 by 300, 300 by 300 mm. So challenge is here, because one cannot make bigger samples. So what we propose later, once we have developed this capability, so we'll try to develop joining strategy, these small pieces, so that one can make a bigger structure. And this kind of work has not been done yet. And once this bigger structure is available, then one can make actual package boxes for loitering munition. So there are 3 stages. So right now I'm focusing on stage 1 only. Later we'll focus on stage 3, stage 2 and 3. So here I have shown our approach for stage 1. So first we'll manufacture, print some materials. Then we'll go for static and dynamic simulation experiment. We'll generate material property, which we'll use for our optimization simulations. And then we'll go, once design is optimized, we'll go for printing the structure, and then we'll perform experiments of combined shock and fragment loading. And if our design is satisfied, then we'll finalize the design. Otherwise, we'll go and revise our design. So these are the two ongoing works here. So these are funded by one of the DRDO lab, DMSRD Kanpur. Here we have simulated blast loading on honeycomb structure, near field blast loading we have simulated here. And we have used here a couple Iranian Lagrangian scheme available with Abacus. And here we have shown the fragment loading on this one. But in this work, we could not benchmark our simulation due to lack of experimental facilities, number one. Number two, here we have used many layers, and we have used Kevlar also. And in Abacus, the damage model available for Kevlar is, it doesn't have strain rate sensitivity, and also it's suitable only for unidirectional fibers. So now we have developed a code for implemented model for Kevlar, which can capture strain rate sensitivity also, and which can be used for woven type of Kevlar. So this work we have done, but due to lack of experimental facility, we could not benchmark our results. So this is our funding requirement. So we want to buy one single stage gas gun with accessories. So this is major fund will go here, and we want to buy one powder bed fusion ultimate manufacturing machine, and then 2 JRF. So this total amount will cost around 2.95 lakhs, including contingency, travel, and overhead. So this is from my side, sir.
Thank you, sir, for nice presentation. So one thing, so can we do this acoustic structure with the metal also?
So this is for metal only, sir. What we are proposing for, because in literature people have reported plastic based also, but those are suitable only for low overpressure and low velocity impact. So here we are proposing metal. So we will try, we will go for steel, as I mentioned, right, sir? We'll try for steel and aluminum. Aluminum setup is very expensive because reflectivity of aluminum is very high. So printing aluminum structure with thin cell wall is quite challenging. So we had to do some pre-processing, and that increases the machine, cost of machine setup. So that's why we're keeping steel also. Yeah.
Thank you. Rajvan, you want to say something?
Yeah, I have a couple of questions, Professor. You have mentioned DMSRD CARS 149. And,
Yes.
Have you had actually material sample fabricated against this CARS, which
Sir, actually
can
here
be
what
tested?
yeah. So this honeycomb we got once manufactured through one of the industry in Bangalore, but they have used welding technology. So the drawback of the technology is that one can pull these. One can open this interface by pulling by hand itself. So that doesn't work actually, sir. So then they realized that we have to go for 3D printing. That is the only way, because Chinese are also doing 3D printing and they have shown very good result actually.
No. At present, can you arrange some samples or not?
Sir, actually honeycomb, 3D
Because
printed
we
samples.
have the ballistic testing facility, and we can actually help you in actually validating that simulation of the model made by you. So if you can give some energy absorption calculations, and if you can give a sample,
बुलेट वेलोसिटी कितना ले रहे हैं?
that can be used as input in this project also.
Okay, sir. So actually, sir, right now we have received some honeycomb made by conventional technique, that welding technology, and that samples are available with us.
Then
And that we can do,
next
sir. That we can do.
Next, I request you to actually include some calculations related to what Indrapal has said, that metal-based exotic structures. Okay, so how the energy absorption is made by them. You can include some literature data, and you can give us a detailed proposal. Okay, the
Sure,
testing
sir.
part
I'll do it,
is
sir. I'll
okay.
do it,
From
sir.
TBRL, testing can be done at TBRL. There is no issue.
Okay, sir. Okay, sir. Okay.
For nice presentation.
That's
Sir, please log off and remove your slides. Okay, thank you. Good morning, Mr. Kamal.
Unmute and go ahead with your presentation.
Mr. Sheikh. Yeah,
Yeah,
please.
am I audible, sir?
Yes, you are audible.
Thank you so much. Let me just share my slides. Is my slides visible, sir?
Yes, visible. You can go ahead.
A very good morning to all of you, respected panel members. I am Dr. Sheikh Mustafa Kamal, Assistant Professor in the Department of Mechanical Engineering from Tezpur University. Today I'm going to present two proposals. The first proposal is on design of blast, shock, and fragment barriers for mitigation of sympathetic detonation. So this work I'm collaborating with Professor U.S. Dixit from IIT Guwahati. So this work actually focus on a pressing problem in the area of technologies for insensitive munitions. So, you know, energetic materials such as explosives are highly sensitive to external stimuli. So when one munition called donor detonates, it can unintentionally trigger neighboring munitions known as acceptors, causing various types of hazards such as blast overpressure, shock transmission, and fragment impact. So therefore, to mitigate such hazards, our aim is to design a barrier system, and the work is based on a simulation-driven framework. So coming to the problem statement, so as I have mentioned that the sympathetic detonation causes various types of hazards, and to safeguard against such hazards, we need a barrier systems, right? So in order to attenuate the blast overpressure and then shock transmission to solids and fragment interception, and we are considering and these are needed for various operational scenarios such as storage magazines, transport containers, and field shelters. So here I am showing a conceptual design of such barrier systems used to be used in such scenarios. So here, if we consider a container, a transport container, or it may be a storage container. So here it is just representative. So what we are going to consider is that each munition will be kept inside a cell like this, and it is surrounded by barriers from all sides. So if they are stacked from the floor, and the roof will also act like a barrier. So here you can see this red color circle. This is the donor munition is a representative, and then this yellow, this blue colored circles represent the acceptor munitions. And then you can see this. I am considering the barrier walls, where you can see that I'm representing like a layered one. I have a barrier, and then I have some air gap, and then space layer basically, and then again the barrier. So here I'm just showing standard of distance 150 millimeter, and these dimensions are just representative. So it can be of any shape and any dimension as per the requirement of the DRDO. And then coming to the barrier materials, so we are going to consider these materials like ultra high performance concrete. From literature, it revealed that this UHPC is actually a good candidate for blast attenuation, which has it has a very good compressive strength and high density microstructure. And then ballistic grade steel such as AR 500, they're capable of resisting fragments. And then fiber reinforced polymers, it may be a carbon fiber reinforced polymer or glass fiber reinforced polymers. They are very lightweight and also actually capable of absorbing a good amount of energy. And so these are candidates, material candidates for our study. We're just shortlisting based on the literature, and then we are also paying our attention to hybrid composites, where we will actually combine the effects of all such materials to enhance the attenuation. And we're going to consider with and without space layers. Coming to the current status and novelty, so most of the current studies actually focus on blast attenuation or fragment resistance in isolation. There is limited research uh, uh, actually that focuses on the combined mitigation of blast, shock, and fragment. Many research actually often relies on empirical testing or simplified models. So our novelty lies in developing a unified computational framework to address all such threats simultaneously, and then incorporating multi-material hybrid barriers with space barriers for enhancing attenuation, and then by using parametric and optimization based design for generating guidelines for future use. And all this makes our proposal as a first attempt to systematically link material constitutive modeling to simulation, and then to design guidelines for sympathetic detonation mitigation. So our objectives are like this. So we are formatting our objective this way. First, we'll develop a computational design framework, and then to simulate blast, shock, fragment interactions, and then to identify effective material combinations, and then to provide design guidelines. And this slide shows actually the interlinking between our objectives. So first we start with the threat characterization, and then we move to the constitutive modeling, and then parametric study, and finally design guidelines. So coming to the methodology, again, the threat characterization. So here actually we are going to consider a group of munitions or explosives. Here at this stage we are actually not considering any specific explosives. Here we need the suggestions of a DRDO laboratory, or we'll also get some guidelines from these references like NATO AOP 39. And then we're thinking to actually consider 4 to 5 explosives for this purpose. And then we'll consider the input hazards such as donor NEQ, blast decay, fragment spectra, and shock impulse. And then we'll also set our thresholds for safe design, such as the threshold overpressure, fragment penetration, and shock impulse. And then we'll also study the material response through simulation. We also can actually develop some analytical or semi-analytical model also for this. So for metals, we are going to use Johnson-Cook model, and then Holmquist, Johnson-Cook, or Drucker-Packard will be used for UHPC, and then composite damage models will be using for FRP with energy absorption quantification. And then we are going to use the simulation tools like Abacus Explicit Solver or ANSYS, and we are going to consider the scenarios where we'll be varying the separation distance, barrier shapes, and layered configurations. So here, as a representative, we are showing some typical barrier configurations. So we'll play with this. Our parametric design approach actually varies thickness, layering, air gaps, and material combinations, and its output will be evaluated against the performance indicators like overpressure, which needs to be less than the threshold, and the residual fragment velocity, it should be less than the penetration limit, and also the shock impulse should be minimized. So we're going to use a physics-based simulation approach. So they are governed by, this is governed by certain equations. So these are the governing equations I've listed here. And then after completion of this project, we are going to deliver a simulation-based design methodology, barrier specification for safe munitions, and then comparative material performance and design certain guidelines for future use by the DRDO for practical implementation. So this is the tentative budget we have considered actually. So as you know, this the work actually proposal involves a high-level modeling. So we need skilled manpower. So we are considering 2 RS with PhDs and 2 JRFs with MTech or BTech. So the maximum fund goes there, so 82.17 lakhs. And then we are also keeping some fund for computational resources, and it's coming out to be 1.2 crore approximately. But this is again tentative. It is not final budget. And then we are going to consider 3 years timeline for completion of this project. So in the first year, we'll devote our time in threat characterization and material modeling, validated against published literature. And then in the year 2, we'll devote our time to develop simulation framework and parametric studies. And in the year 2, we'll actually optimize our design considering various materials combination and performance parameters, and we'll also provide a design guideline. So this is actually the because it is a collaborative work, so this share of works between Tesco University and IIT Guwahati. And to conclude, so sympathetic detonation actually is a it poses a major risk. So our simulation driven approach will help in arriving at a suitable barrier system that can mitigate such hazards due to sympathetic detonation, and this will be useful in storage, transport, and deployment missions. So with this, I conclude the first proposal, and next I'm moving to the second proposal, and this proposal is on design of composite materials for package boxes to mitigate blast loading. And again, this is a collaborative effort with Professor U.S. Dixit from IIT Guwahati and our international collaborators, Professor Anis Roy and Dr. Konstantinos from Loughborough University, UK. So, the safe transport and storage of sensitive payloads such as explosives or defense materials or hazardous goods, they require packaging that can withstand accidental blasts. And the current packaging design is not often considered actually the blast attenuation is not done considering blast attenuation in mind. So that may lead to the risk of secondary explosions. So our aim of this project is to design, model, and evaluate composite material package boxes to mitigate blast effects. So we are going to consider 3 key approaches: careful material selection, then mesostructure design, and numerical simulations using Abacus, ANSYS, or LS-DYNA. And coming to the significance and motivation, so accidental detonations can be catastrophic, not only for payload safety, but also for human lives and surrounding property. And the actually traditional wooden or that metallic boxes or metallic containers, they either fail suddenly, or the blast load is directly transferred to the payload. So here the rule of composite comes in. So this composite actually provides us flexibility. They allow us to tune stiffness, density, and failure modes. And then we're also going to integrate passive design strategies such as graded impedance, sacrificial layers, and or even controlled fragmentation. So this is our objective. So our proposal actually consider to propose and evaluate 3 to 4 composite box architectures, and then develop and validate numerical models using Abacus, ANSYS, LS-DYNA with in-house subroutines where appropriate. And then we predict and compare the performance indicators such as transmitted pressure, impulse, and payload acceleration. And coming to the approach and methodology, we'll first start with the concept generation and down selection. Then we'll proceed to material selection and mesostructure design. And then we'll do the numerical modeling and simulations. Then we'll conduct a sensitivity analysis. And finally, we'll provide the design guidelines. And our concept space include actually solid fiber panels, hybrid laminates, sandwich panels, lattice cores. The sandwich panels are very effective because due to their core crossing and delamination properties. And in the lattice cores, they are very lightweight and also tunable. And in hybrid laminates, you can actually combine the properties of various fibers, and we can take the advantage of that. And based on the requirements, we can actually shortlist 3 to 4 best performing composite architecture for detailed study. And then this is just representative. I'm showing some architecture. These are actually shown in literature. I've taken from literature, but again, we have to play with this. And then but coming to the material selection and microstructure design. So the candidate fibers include glass, carbon, aramid with thermoset and thermoplastic matrices, then core materials include flow foam, lattices, and even auxetic honeycomb structures. At the meso scale, we'll focus on graded density layers, fiber orientations, and engineered defects to promote energy dissipation. And one of the interesting approach is actually auxetic concepts. So we're also thinking to explore that use of auxetic materials for this purpose. So these auxetic materials have negative Poisson's ratio, and when you stretch it, expands in the lateral direction. So this actually feature or this property of auxetic materials will be useful in attenuating the blast loading. And then coming to the numerical modeling and simulation. So here again, we're going to use a physics-based approach, which are governed by certain equations. So for blast loading, we're going to use Fred-Miller equation, Hopkins and Crunch scaling. And then for modeling of composites, we're going to use classical laminate theory. Gibson-Asbury relation will be used for foam crushing modeling. And then coupled Euler-Lagrange and momentum equations will be used for fluid structure interaction. And simulation tool includes Abacus, ANSYS, LS-DYNA. So the systematic workflow goes like this. So first we'll develop FE models with advanced constitutive material models. Then we'll apply blast loading using pressure time histories or FSI solvers. Then we'll extract performance matrices such as overpressure, impulse, acceleration, and damage. And then we'll conduct the sensitivity analysis considering by varying layer thickness, density, fiber orientation. So after completion of this project, we're going to deliver validated numerical models for blast attenuation, optimized composite structures, and design certain guidelines for future use. So this is the tentative budget. Again, the budget is similar to the first proposal. Maximum budget is for the manpower, and then we're actually considering the travel on a higher side for collaborative visit and conferences. So that's how it comes out to be approximately 1.4 crore. Again, this proposal is considered to be completed in a 3 years timeline. So in the first year, we'll be doing literature survey and baseline modeling, validated against published literature. And then in the year 2, we're going to do advanced simulation and parametric studies. We'll do parametric studies, then optimization configuration for maximum energy absorption and maximum weight. And then the third year, we're going to do the detailed comparative study and sensitivity analysis. And finally, we'll provide the design guidelines. For actually conclusion, if we're going to the conclusion, first I would like to highlight why we are collaborating this work with our international collaborators from Labrador University. Because apart from the expertise available with the Indian PIs, actually both the PIs work in the areas of solid mechanics, particularly in advanced computational modeling involving plasticity and high strain rate. Apart from that, actually, our international collaborators also has expertise in modeling modeling actually ballistic impact and all. So recently they also work a study on the effectiveness of explosive reactive armor against the penetration of long rod projectiles, which is directly relevant to this proposal. So these are some indicative relevant works from our collaborators. And then I just would like to show some simulation work from the last publication of our collaborator, which actually here you can see projectile is a tungsten rod impacting steel witness plate. So here you can see, considering a standoff distance of 100 millimeter with a 60 microsecond detonation delay, the long rod tungsten projectile impacting steel ERA package with witness plate. So this is just to show you from their earlier work. So they have done some work in this direction. So this collaboration will be useful. And then coming to the conclusion, the composite package boxes actually offer a transformative solution for survivability under blast loading. then our integrated design approach will ensure robustness and reliability, and ultimately it will contribute to safer transport and storage of hazardous metals. With this, I'd like to conclude. Thank you. Thank you so much for your attention. If you have any questions or suggestions.
Thank you, sir. Rajvan.
Yeah, Professor, I have a couple of questions. First, I think you must differentiate between whether you are dealing with blast, shock, or fragment. All the
Sir,
problems needs to be actually dealt with individually, and then
yeah.
you progress further to collectively address this problem.
Yeah, our approach is like that only, sir, because from literature we have found that actually whatever literature is available now, they actually either considering blast loading or fragment separately. No literature is found where they consider the actually mitigation of all such hazards altogether.
Yeah,
So
that
our approach is first
is
will,
why
yes,
I
yeah, our
just
ultimate aim is to actually mitigate the simultaneous hazards, all such blast, fragment, and this shock wave mitigation, all this actually.
in
Finally we'll achieve that actually.
in because you have actually starting the studies now. So my
Yeah.
suggestion is you address first the maybe blast problem. Okay.
Yes, we'll do that. First we'll see individual effects, and then
Frequently, maybe
we'll
these two we can go
yes,
to.
yes, yes, sir,
And
yes. Thank
second,
you for the suggestion. Yeah.
PIs, maybe Vishal can comment whether they are allowed and what will be their role if they are allowed. So that has to be specified. Foreign PIs. Vishal, you can clarify a little bit.
Sir, regarding foreign PIs, even yesterday, I think Jyoti sir also mentioned that till now we are not allowed to work with foreign PIs. They can,
Okay.
I think, even as a co-PI, they might, but still I'm not sure.
So that has to be checked.
That has to be actually.
Okay. Okay.
Then I suggest that some literature data on the design using different
Okay, sir.
materials that can be included in the proposal, detailed proposal. Okay, not
Yes, sure. I'll include, sir. Even because it is a preliminary presentation, so considering the time lead, I have not included, sir.
You have a good idea of the things. There's no issue, and then you can include any samples which will be delivered at the end for maybe testing and validating your simulation and all that. Okay.
Yeah, actually, yeah, we are keeping the experimental thing for the next phase. Actually, means maybe after
No, no.
because if I take a project, then I have to deliver
Possible,
also.
he will be agreeing for giving a proposal.
Yeah.
So
Okay,
in
sir.
that
Thank you,
you
sir.
have to include at least some samples for
Sure.
validating that.
Yeah. Okay, sir.
Yeah.
Okay. Okay.
Mr.
That
Kamal,
part
one
will be.
part from my side. So you are
Yes, sir.
mentioning that concrete as a transport carrier. It is very odd choice because it will create problem for strength as well as the weight constraint on the transport carrier. In the first
Okay, sir. So
proposal,
that's
you have
why.
mentioned this
Yeah.
concrete as a
Yeah.
transport carrier.
Yeah, no, sir. Actually, we are just considering. I'm just mentioning the scenarios, say storage or that transport container. But we are considering a pool of materials. So even we are considering FRP and then other materials as well. So depending upon the requirement, we're going to use the materials. We'll see that feasibility. We'll considering the weight also.
Uh, because that can be considered for some other application,
Yes,
mostly
yes.
for
I
this
understand, sir.
storage magazines, not for this transport as a concrete. Okay,
I
sir.
understand.
Thank
Yes,
you.
concrete. Yes, sir. Thank you so
Thank you
much, sir.
for
Thank you.
nice presentation.
Thank you, sir.
Sir, Dr. Ragappan, you are there?
Are you able to hear me, sir?
Yes, we are able to see and hear you. Please
Yeah.
go ahead.
Good morning, sir. So today's proposal presentation is titled as fortified concrete, which is specifically for bunker applications where you have storage of ammunitions or explosives. So it is one of the proposed area in the web document was on design for sympathetic response. So it falls under design of blast, shock, and fragment barriers. So the PA for this proposal is Dr. Piyush Shansali. He works in cement chemistry concrete. Right now, he is out of the country on travel. So he will be joining, but I'm not sure. So I am Dr. P. Alagappan. I'm from structural engineering background in civil engineering department. So, yeah. Yeah, so just a brief introduction about we are specifically focusing here on ultra high performance concrete. This project is going to be purely experimental work where we come up with a ultra high performance concrete. So just to give a brief introduction about it, it has been widely used across the world. The main difference between the ultra high performance concrete versus conventional concrete is about how densely the particle packing is there. So you can see the image, two images as a comparison side compared between conventional and UHPC concrete, where we can see it is densely packed and it has an ultra low water to binder ratio and very high binder content. To just give you an idea on what is happening, how we achieve this ultra dense microstructure is to do a optimum particle packing. There are various models for it on how to achieve at this optimum packing and have an ultra low weight water to binder ratio, which varies from 0.14 to 0.22, and high binder content, which can go up to 1200 kilogram per meter cube. And to add tensile strength properties to it, we add steel or synthetic fibers, where the ratio varies from 1 to 5%, which imparts the ductility behavior to the concrete, which is also one of the important things when you want to design panels which is made up of UHPC. So main highlight of this UHPC, why it is very popular when it comes to this high strength, is about high strength. So compressive strength is typically in the range of 120 and it can go up to 680. And tensile strength is also in the range of 5 to 20 MPa. And one of the most important thing is also about durability. Since particles are packed very well and the permeability is very low, it can even last for 100 plus years with very minimal interference with the service and other activities. So just to walk through the procedure of this UHPC, typically we have powders and sand, which is slowly mixed and then mixed with water, and then water retaining admixtures are getting added, and then we mix it at higher rates and add steel fibers and then aggregates depending upon the strength we need, and then we get this mixture. This is the overall flow on how we generate this UHPC. So the overall process looks a little bit straightforward, but you can see from the literature, this is a compiled literature of very recent articles. You can see that how much the density strength can vary depending upon how you play around with the various constituents which you are mixing together, and cost also obviously plays a role. And I want to specifically highlight this car tuff which is shown here. This is one of the designs which was made by US Army Corps of Engineers, specifically which was developed for the blast and impact application, where they were able to achieve the strength of around 200 MPa. This is their army related mix. So likewise, if you see in literature also, the common average of compressive strength is typically around 100 to 150. One or two cases where you can see that it has gone up to 680 and above 200. So this is just to give you an overall idea of what is the current state of the art when it comes to literature. But as we discussed, it is about final implementation or final application of it. Why it is much more popular when it comes to our application is about the property. So you can see here the comparison between conventional concrete, which is the dotted one, versus the solid one, which is the ultra high performance concrete. And you can see the top one is for compression and tension. So here we can clearly see how better it performs into the overall strength of the concrete. In addition to strength, you can see that the strain at failure also is increased multifold. So for example, in compression, it is almost twice the failure strain. Whereas in tension, you cannot even compare. It's very high compared to the conventional concrete tensile strength, which is typically weak. Because of the fibers which we add in UHPC, it is very high. And it is one of the important property for fragmentation, penetration, and the overall impact performance of this UHPC. So coming to the individual property, we can see the static strength typically varies between 150 to 200, 250, which is the common range worldwide. And dynamic or blast response. So it has a better high strain rate property. It has better compressive strength. And this increase in the strength also helps us in having a better fragmentation penetration when it comes to the tensile strength property. And toughness and fracture is also multifolds higher compared to the conventional concrete. And the durability and life cycle. So for example, in inaccessible areas where you want to storage ammunition, where the freeze and thaw cycle alternates between it, this ultra high performance concrete gives a better performance compared to the conventional concrete. So applications wise, what we are specifically focusing here about blast resistant panel is what been shown in literature. And it also used in the literature, it has been widely used for bridges. In fact, in India, there are only 2 players in a commercial level who makes this UHPC. So it is also started using in bridge decks, and a few applications they have started using UHPC. One of the other important thing is about economical and sustainability benefits. So embodied carbon content is carbon dioxide is very low. Life cycle cost, as I told you, it lasts longer. In overall life cycle cost, if you see also, it will be relatively have a better savings. Maintenance, as I told, since it is highly impervious, the permeability is very low. It also has no penetration or acid attack or other things, chloride, sulfate attack won't happen, which helps us in having less maintenance which is required for this UHPC. So coming to the main objective of this proposal, so what we are proposing is we are proposing to develop a UHPC which can attain a minimum compressive strength of 250. That is going to be our target for this proposal. As I told, even though commercially it is available in India, so if you see commercially it is around 150 is the targeted compressive strength that has been claimed. So long-term strength it might increase, but here we are talking about specifically about 28 days strength of it. And we are also focusing on a tensile strength of around exceeding around 20 MPa and elastic modulus surpassing 70 GPa in a cost effective manner. That is also one of the most important things which we need to consider, because you can see in the existing technology, the UHPC costs around 70,000 rupees per cubic meter. So even though it resides in thinner sections, the overall cost will be higher if you go with the commercial on what is available. So what we are trying to propose is coming up with a cost effective way, at the same time achieving the strength of 250. So main target is going to be 250, which we'll try to see how we can negate with the cost perspective also. So what we are proposing, how we are going to approach this proposed UHPC where we achieve a tensile strength of maximum 250 is playing around. As I told, there are various components into the UHPC, where ordinary Portland cement and you have silica fumes, quartz powder, and then fly ash. So we need to optimize what is going to be the configuration. Even though literature gives some range, we need to exactly come up with what will be the range which will be working for our specific applications. Likewise, water to binder ratio, the range is around 0.16 to 0.2, which we need to. So this is where most of the optimization will come into play. What will be the extent of superplasticity which we add? What will be the fiber reinforcement percentage and the curing protocol? Once the concrete has been made, how do we cure it? And finally, particle packing, we are going to use Andreessen and Anderson curve, where the factor is going to be 0.22. So we are going to optimize these parameters and then come up with various UHPC samples, in which we will try to do both mechanical strength related to compression, splitting, tensile, flexure, and also impact testing. And also we will be doing durability test. As I told, that is permeability is one of the important factors in it, which will help us in giving lasting for a longer time. So where we'll have rapid chloride permeability, softwidity, and carbonation test, which will be carried out. So this is the overall budget. It's for 2 years. This project is initially for 2 years. So the overall cost is coming around 2.27 crore. And the timeline for activities, in first 12 months, we will come up with the development of ultra performance concrete. We will arrive at what will be the optimized mix design, and which will achieve the targeted strength of around 250 MPa and tensile strength of around 20 MPa. And next 6 months, we will try to do ballistic blast and ballistic impact testing, using shock tube, and also on using projectile impact testing to see the evaluate the performance of the ultra high performance concrete which has been made. My final target is we will finally come up with a panel which will be meeting the objectives which we have set. So where this can be used as a panel, and the next phase of the project, we are planning to take it as a wall. How can we assemble these panels in terms of what will be the optimum thickness? So that will be the next phase of the project which will be taking up. But in this project, we will deliver a panel which will have the performance which we have mentioned here. So these are some of the references. Thank you.
Thank you, sir. Rajwan, do you have any point? Sir, I have some few points.
Yes, sir.
So this is a new type of concrete we are not talking about. So as you have shown in the literature, people are going up to 600 also.
Yes, sir.
So why we are stopping at 200? Not going
Exactly,
ahead.
right questions. As I told, 600 we can go. The cost of it is going to be very high, sir. So as I told, if you replace your aggregate with the steel or something like that, then obviously we can achieve higher strength and binder ratio. But our worldwide, if you see commercially, well, even in US, commercial available maximum strength they have gone is around 300 MPa. 300 to 800 is within the army and it is in the closed circle only they will work around. So you cannot see vendor commercially giving a strength of about 300 even in US. So that is why our first target right now, if you see what is commercially available is around, we also need to see about the scalability, right? That is one of the most important factor. So in India, as I told, only 2 players are there where they have achieved around 150. So that is why we will target 250 MPa and then come up with an economically viable solution where it can come up with the panels and panels which will help us in reducing the current existing wall thickness and things like that. So that is our first target.
Okay, sir. Second point is there, sir. What are the ingredients we are using? It is a imported or a indigenous?
Indigenous only. That's what that is why we are trying to do mixed design completely. So where majority of the things what you are going to use, except that's what, as I told, we unless we come up with an additive. I'll go to the slide where we discussed about this proposed. So here the super plastics is here now. Most of the companies in India itself is manufacturing it. So most of the things what we are targeting is indigenous only.
Most of means still we have some imported particles.
So that's what, sir. With the existing one, we are able to do it. So until there are imported parts are also available, but whether we are going to use it or not, we will not know. But as I told, all the things are indigenous, which with the indigenous thing itself, we will be able to attain around 200, 250, around, less than around 200 MPa. But to achieve around 250, we will also try to see Indian players, whether they will be able to supply these things.
Sir, at present, as you mentioned, the cost is like very high as compared to the conventional.
Yes, exactly.
So how we are expecting that in future it will come down so that when we go for the mass scale, then it will be very, very costly. No one will be happy.
That's what, sir. The thing is, if we come up with a mass scale, so this ultra high performance concrete has a specialized equipment for making it. So what we are trying to achieve in this proposal is we are also going to take into account that also. How we are going to take into account is, for example, in UHPC there is something called a dry mix. So what we can do is we can do the mix in the site with the dry, and then you can take it to the site and then mix water and then you can do it. That is already been done. So if you do something like that, then even in inaccessible areas, if you want to store anything, it will be easy to construct and things like that. So that is what we are targeting in this one.
Okay. Second, another last from my side. So it will easy to construct make this complete, or it will require some specific or special team only, because in India, as far as you were mentioning, nobody is using this. So how to later on?
Yes, sir. As you said, exactly. That's one. That is why what we are trying to do is we are trying to come up with a mix strategy also. As I told, we will have a dry mixes which will be designed in the facility where technical person are there. Once this dry mix is ready, you can take this dry mix to the site wherever you want to construct a wall or you want bunker or something like that. You can just mix it with water and then you can do it. So we need not have a very specialized team at the site for it to execute.
And Rajman, any point from your side?
Yeah. Have you, sir, have you done any basically feasibility studies on design part also? So how you will be designing basically?
So as I told, the PA is the one who is involved in the cement chemistry and concrete, sir. So he already has a prior experience. So that is based on that, and we already have seen. I already shown that literature is also wide data is available. So it's not that it's not.
Indian survey, you have done a very excellent literature survey, I would say. But I was looking for any feasibility part. So how you will be addressing the issue?
So that's what, sir. That is going to be the first year where we are going to see. So the literature is shown.
Maybe,
Yeah, Piyush.
maybe
Yeah, he is. I think he has joined. I think
I just joined, sir. Sorry, I was traveling. I was in Vietnam for a travel. Just got back. The two parts. One is, we would really like to enhance the strength currently UHPC has, which will help us design structures more efficient, like in a more efficient way. And also, as Dr. Algappan pointed out, the cost part, because that is currently roughly 10 times the existing, like normal RMC, ready mix concrete. So how can we optimize the cost? How can we further reduce the cost using the indigenous material? All the materials we are talking about are the indigenous materials. So some optimization will be there. That's where we think we can do some interesting research so that we can push the barriers.
Okay, sir. Thank you for nice presentation.
Yeah, thank you.
We'll definitely discuss in future regarding this.
Thank you.
Okay, thank you.
Dr. Prashant, are you there?
Yes, sir. Can you hear me?
Yes, we are able to hear you. Please.
Just give me a minute. I am sharing my screen. Sir, can you see my screen?
Yes, we are able to see.
Sure, sir. Is it moving, sir?
Yes.
Fine. So, good evening, everyone. I am Dr. Prashant Rawat from Department of Aerospace Engineering, IIT Madras. My proposed topic is bio-inspired blast-resistant composite packaging materials. So here I am going to address two aspects as per the sheet. Point number 22, auxetic structure for package box to mitigate blast loading, and composite material for package box to mitigate blast loading design report. Here in this particular proposal, my co-PIs are Professor Algappan from Department of Civil Engineering, IIT Madras, Professor Rajesh Ji, Department of Aerospace, IIT Madras, and Dr. Pradeep. So Professor Algappan is expert of blast experimental as well as simulation based in studies. Professor Rajesh Ji is gas dynamics person. He has a lab where like high speed gas gun setup and all those things are there. And Dr. Pradeep Seshadri is a dynamics modeling expert who are going to be part of this particular project as OPI. So as I already pointed out that there are going to be 2 points which we are going to address here. So what we have observed after going through the literature survey that blast resistance boxes are actually mostly made by monolithic heavy materials, or if it is auxetic material design, mostly honeycomb structures or some other commonly conventionally used auxetic materials are being used. They have very limited energy absorption capabilities, as well as they are sensitive to catastrophic failures in whenever blast happens and like the waves are propagating from the multiple direction. It is difficult to avoid this catastrophic failure, especially in the composite boxes. So what solution we are proposing here? We are proposing a lightweight sandwich panel and auxetic structure which is bio-inspired design, and that bio-inspired design is absolutely novel in terms of studies. So here we are going to take inspiration from cuttle bone. Cuttlefish is a very unique fish which carries a bone in its body as a spine, and it has very good unique features in terms of withstanding with very high atmospheric pressure up to 600 meter of depths in the sea. And we have studied and investigated the characteristics of this particular bone. We have found the porosity level is very high, it is stiff, and it has evolved to withstand with very high impact compression as well as blast kind of situations, like we have been proving it. And we, after investigating on the particular fish bone for 2-3 years. So overall conclusion could be this bone structure is very lightweight, porous auxetic designs which could be useful for high compression, impact, or blast loading situations. So here this is the literature survey which has been done previously by very few groups where they have characterized the bones specific parameters, and they have investigated the cross sections. They have investigated the pillars or like the fundamental aspects of the particular design of the bone, so that they can show that this particular auxetic structure can perform better as compared to conventional existing design. So in particular investigation, what we have observed after going through the basic fundamental level studies, this particular bone actually is a combination of multiple chambers or channels in its structure. So here this CT scan shows that it has the bone which we have studied is had 51 particular number of channels. All the channels were very planned and organized. If you see the cross section of the channel, they have multiple chambers made of pillars, and these chamber pillars are combined as a laminate structure, one over each other. That's how they grow over the edge of the fish. So the cross sectional view shows that these channels are actually aligned in a particular wavy pillar pattern, where the possibilities of like ventilation as well as directional collapse is controlled by the thickness of these wavy pillars, which is going to be key contribution in terms of designing a novel class of auxetic material, so that we can control or trigger the collapse mechanism to avoid any kind of catastrophic failure. So after going through this particular investigation, what we have observed that in our lab we have conducted the compression loading at various strain rates in our lab, and have seen that once you compress it at various strain levels, we have observed that the collapsibility up to 80% strain, this bone withstand or shows the constant value of the stresses that are being generated, or force values. I'll show it in next slide. However, here in DIC analysis we have shown that proven that up to 80% directional collapse start happening under any kind of loading situation. So what we have done, we have extracted the parameter of the auxetic pattern and design, based on which we have scaled the model up to 50x is designed like at multiple scale levels. So here in this particular diagram shows a scaled up 15x model, out of which we have taken a very small section and tried to prove the concept by showing compression impact as well as blast loading, how is it going to react for it. So here this particular model is a 4-chamber model, which is 15x, as I already mentioned, shows the compression characteristics. So only one result has been shown here, so that we could prove that up to 80% of compression or 80% of strain shows 50 plus megapascal compressive results. So these are the results where you could clearly see that while collapse is kept on happening, or compression of the bone or inspired design is kept on happening, is going to show constant value of the stresses which are being generated. And this is the actual requirement from an auxetic structure. And here the best part is by studying and we have observed that once you try to mimic this particular structure, not only control in the design or the direction of the collapse is possible, however by tailoring the parameters, specifically the channel width as well as this entire chambers volume and section, you can trigger the mechanism as per your requirement. So if you want this particular section to collapse from bottom to top, it is possible. From top to bottom, it is possible. Even in some specific situation where you don't know whether which side of the loading is going to create collapse, so you can simply trigger this collapse from middle section to the top or bottom sections. So all these things we have been doing in our lab, and we have proven the concept. So overall, like, this channel is capable of using as an inspiration to design a box. And what we had done after proposing this particular proposal or problem statement, we have done some preliminary studies in our lab, where we have done compression test, as I already shown, and did some very small scale TNT explosion to see how this particular section is reacting as compared to conventional existing design. And this particular modeling was done with aluminum alloy TNT, very small mass, as well as like we have done it in explicit ANSYS dynamics simulation software. We had considered 3 cases, where one case was simply sandwich panel with the conventional walls, as well as second model was only considering one particular chamber. Third model was considering 2 chambers combined together to see how energy is going to be dissipated under blast loading. So here are some results which are being shown, that as compared to the conventional design, multiple channel is more capable of showing stress distribution, as well as directional collapse happen. So here I am showing the limited results, but undoubtedly we are capable of proving that even under blast situation or loading kind of situation, this particular small component, which can be a part of entire box, is capable of loading or providing auxetic characteristics, directional collapse, avoiding any catastrophic failure under such kind of loading conditions. So these are the stress analysis I have shown. So as per the proposal timeline, we have subdivided our proposal, 3 years of proposal, into 6 months of period, where identification of the principle as per the actual requirement of DRDO are going to be considered, and we are going to tailor our parameters which we have extracted as per the requirement depending upon the loading conditions or situation. Then we are based on those parameters, we will be performing numerical simulation to prove that this design is going to work. And then we have like 3D printing facility from polymer composite to metal composite materials. We are going to print the exactly same design scaled up model, and after proving it at the coupon level, we can go for integrated box design and development. And ultimately, in the end of the day, the sandwich panel is going to be designed, and a report is going to be transferred, which is going to proven for impact, high velocity impact and blast kind of loading situation, followed by a report writing. So that's how we are going to take up this project for 3 years. And here is the budget of the proposed proposal. So we have subdivided it into two problems. So for that we need manpower, as well as we have to develop a specific or tailor specific input parameters in impact setup as well as blast loading setup. So we are going to have like integrate such kind of facilities along with damage investigation and design development part, which is already there in the picture. So entire project, including 20% overheads of the institution, is going to cost me 3.29 crores. So that's it from my side. Thank you so much, sir. If there are any questions.
Thank you, Professor, for presenting a very nice idea. Rajwant. I think he's not available. Sir, I have 1 or 2 points.
Please.
So, as you mentioning, the conventional material are not multi-directional, but this structure is also for unidirectional only, not for the multi-directional application.
Sir, multi-directional application would be, sir, blast loading is a multi-directional loading. Here, multi-directional means if you can think of this particular panel, it can perform from this design as well as from backward design.
So that is the only single direction only, and either from the top or bottom, not the multi-direction. We cannot say like that. Multi-direction means any direction, X, Y, Z. It is only X.
Sir, here if you see, this blast loading is actually loading the specimen from multiple direction, and the impact that we have planned particularly is not going to be only transverse impact. It is going to be like oblique impact condition, as well as while testing this design against the blast loading, we are going to incline the panel in different direction. So we are going to prove it at 90° as well as other directions as well, sir.
So this structure is mainly for blast application, I think not for fragments. So you have to add something for fragment protection also.
Sir, fragment protection is covered with like a high velocity impact loading situation where small fragments are going to collapse or like going to bombard this particular specific structure, sir. So that's how we are trying to cover that thing.
So here we will take this structure as a base, and we would use any either polymer or as a metal you guys are proposing to make this structure.
So this structure is going to be made by metals, sir. Metals or like high class of alloys, using 3D printing specifically, because as such in today's scenario, this design cannot be fabricated by any other mean than 3D printing.
But sir, but later on, if we go for the large scale, then we cannot rely only on 3D printer. Then how to make this type of structure in future for large scale?
So for that, sir, you can make such kind of design at, like as I have shown you here, some small, sir, some multiple section you can make by other conventional method of metal casting or molding methods, and then you can stack it together if you need to fabricate it at larger scale, sir. But for our
Okay.
investigation, we are going to use 3D printing techniques, sir.
Sure. Thank you, sir, for a nice presentation and new idea. Thanks.
Thank you.
Once
Thank you
again.
so much. Thank you, sir.
Dr. Sogata, are you there?
Yes, sir. Yes, sir. I am here,
Yeah,
sir.
please.
Sir, are you able to hear me, sir?
We are able to hear you.
So, my screen is visible, sir?
Not, we are not able to see. Yeah, it is visible now. Hello. Dr. Kumar.
Yes, sir. Yes, sir.
Yeah, it is visible. You can go ahead.
Yes, sir. Are you able to hear me, sir?
Yes, we are able to hear and see you.
Good morning, sir. So myself are from NIT Rourkela. Yeah, okay, sir. Okay, sir. So our proposal is for the design and development of the signal conditioning module and data acquisition module for blast pressure measurement. So using piezoelectric pressure sensor. So myself, Dr. Kaur, and my co-investigator is Dr. Sudeep Kundu. We are from NIT Rourkela. So the motivation. The motivation for this proposal is basically that we, the current PI and his team, myself and Dr. Kundu, is currently undergoing one project under ARMREP. So it is the gun chamber pressure measurement in the range of 1000 megapascal for, you can say, the electronics module we are going to develop the first. So it is a 4 years project, and it is currently 2 years, just 2 years over. And we have developed a first prototype for the gun chamber pressure measurement, which has a larger range. It is 1000 megapascal. And this problem, this blast pressure measurement is also in the similar direction, but the pressure range may be a little bit less compared to the gun chamber pressure measurement. So that's why, and this range can be variable. We are not exactly, you can say, exact pressure. We don't know, but we have searched, and from the literature survey, we have seen that the pressure, this blast pressure may be in the range of, you can say, 50 to 500 psi. So the challenge in the development is that in this signal conditioning module, we want to develop the signal conditioning module as well as a compact data acquisition system where the multi-channels will be there. So the challenges are basically we have to select the proper sensor. The sensor mostly for this kind of application, this high pressure measurement, the sensor mostly supplied by either Kisler or PCB Piezotronics. So in our current application, we are using the sensor from the Kisler, but we can use the sensor from the PCB Piezotronics also. We have to select that particular sensor which has the actual range of the detection. Then this signal conditioning module is basically, it should be battery operated. Mostly the battery is, we are using 3-volt coin cell battery. So it should be a battery operated system. So you can say its power consumption must be low. And along with that, we have to store the data because as it is a battery operated system, so then this complete system will be exposed or will be, you can say, placed inside the gun chamber or the blast location, whatever may be, and then we'll recover those modules, and then we can retrieve the data from that module. So the data storing capability must also be there. So, and also, if we want to build a data acquisition system, multi-channel data acquisition system, where 4 or 8 or maybe as per the requirement, the number of channels. So, if we want to place the data acquisition system close to the blast location, maybe a few meters away from the blast location, so short cables will be connected with the sensors, and that cables will come to the data acquisition system, and it will acquire the multi-channel data. And then we will, from the data acquisition system, multi-channel data acquisition system, we will be able to recover the data. Now, So this measurement of blast pressure, it is important because this analysis, the pressure profile, whatever you are getting, it causes the damage to the surrounding structure. So it is as well as the human being also. So this measurement of this peak pressure, the pressure duration, pressure pattern, pressure profile. So those important parameters from the you can say pressure measurement we can find out and we can analyze the pressure related data. So this objective of this proposal is that we want to develop a signal conditioning module for the blast pressure measurement to record the blast pressure and the plot accurate, you can say the pressure time curve we want to get it. Then it can be a single module or it can be a multi-channel data acquisition system. We also build a multi-channel data acquisition system where can be 4 or 8 or 12 data, you can say sensors can be connected. And that complete multi-channel data acquisition system, we want it will be able to record the data. And we want to develop the required software, you can say package to retrieve the data, to collect the data, as well as so during, you can say, the deployment of the sensor, we can program it also. Means for an example, what will be, you can say, the limit of the peak pressure. If there is any threshold we want to set, that can also be set. How much duration of data we want to store, what will be the standby time or the sleep time. So those things of, you can say, the parameters we can set before deployment of the module or the sensor. So these are the typical specification based on the literature survey or based on our knowledge, whatever we have searched. So the pressure range may be within the range of 50 to 500 psi. It may be more than that. But your pressure sensor must be able to, you can say, acquire or the sense the data within that range. Now, most of the cases, this kind of blast or high pressure measurement, the sensor is of piezoelectric type. That means it develops the charges based on the pressure. The charge has been developed, and its sensitivity, if you look at it, it is mostly picocoulomb per, you can say, the psi or per megapascal or per bar. So those kind of specification will get it based on, you can say, certain 1 or 2 sensors, example sensors. We have gone through the PCB piezoelectronics as well as the Kistler also. Based on their, you can say, sensitivity, we have just multiplied with the sensitivity, and it can be 1000 picocoulomb of charge can be generated. The temperature range may vary, but we thought that it can be the range. It can be changed also, and it also depends on the sensor and it's the acceptable the temperature range. So the resolution of the data, what we'll store, it is basically will be of 12-bit resolution, and the memory capacity for each of the module may be the 10K bits. The 10K watts or the 10K data samples will be stored within the memory of the system. And the measurement time, the total measurement time may be 5 milliseconds. In our gun chamber measurement, it is mostly 100 millisecond. But here, the measurement time can be little bit more as per our understanding. But that can be, you can say, to make with the discussion with the RBLAD. Now, these are the typical specifications we want to follow. And then the deliverables, the first one is a single, you can say, signal conditioning module with the sensor. The sensor we don't want to develop. Sensor we want to purchase from either Kistler or PCB Piezoelectronics or any other vendor which can be available in the market. And then we want to build one 4-channel data acquisition system that will be a multi-channel data acquisition system we want to build. Now, so if you look at the conventional blast pressure measurement system, there the multiple sensors are connected, and most of the cases we have seen that pencil probe type, you can say, the sensor arrangement is being done, and from there a long cable is connected to a data acquisition system which is placed in some distant location. It can be 100 meters or it can be 200 meters also. Now, these piezo sensors are, you can say, it generates charge, and that charge can be converted to equivalent voltage by means of certain signal conditioning module. Mostly the charge amplifier is being used. Now, if you want to, you can say, if you want to connect a long cable, the capacitance of the cable comes into the picture, and this actually signal attenuation occurs because this capacitance, the cable capacitance and the resistance, it forms a low pass filter, and those kind of you can say data loss is there, and that's why most of the conventional data acquisition system which are the most of the data acquisition system which are being placed at a long distance, then the constant current transmission is being preferred. Here, so from the sensor itself, the voltage is converted from the sensor, the data, the voltage, whatever the data acquisition system is there, the voltage is converted to equivalent, you can say the signal is being transmitted by the constant current supply. Then at the data acquisition system, the signal is again recovered by a decoupling capacitor. So that's why we cannot transmit the voltage directly because of the large capacitance. The constant current transmission is preferred. So this is the current conventional. You can say the current can be the 4 to 20 milliampere. So in most of the, you can also say that most of the, you can say process instrumentation also, the current transmission is preferred instead of the voltage mode transmission. Here, the conventional, you can say blast pressure measurement system, they basically prefer this current mode transmission because the cable capacity, because of the mostly the cable capacitance. Now, in our proposed solution, the first solution we want to propose is the individual sensor. We want to build a micro module, a electronics module, which will be attached with the sensor, and then it will be placed in a suitable casing metal enclosure, and that will be placed into in the near the blast location. So a single sensor and a single electronic module that will be placed within the enclosure, and that module itself will be able to store the data so that we don't have the necessity of any cable connection. The sensor, the electronics module, we want to develop it, and that will be directly, you can say, connected to the sensor, and the complete system, the sensor and you can say the electronics module, what we want to develop, that will be placed within an enclosure, and that will be placed close to the blast location. Now the second solution is, so it is the single, you can say solution, single sensor, single module. Now we can develop a multi-channel data acquisition system where we can connect. Here we have, so I have shown the 4 sensors. It can be more than 4 also. So there the multiple sensors will be connected to the data acquisition system. And we will develop a data acquisition card itself. So it is mostly, you can say, if it is a 4 channel, then 4 such kind of electronics module will be integrated in a single module, and that will be placed within an, you can say, the metallic enclosure. And then, so there can be some, you can say, USB, you can say the data, through USB you can collect the data, or any other, you can say, data retrieval mechanism we can have. So there are 2 solutions. One is the single sensor and the module, and it is a multi-channel system. These 2 solutions we are proposing in this proposal. Now, so mostly in this proposal, we want to develop the electronics module. So electronics module, as we all know that these sensors are basically piezo sensors. So charge is being generated. That charge must be converted to equivalent voltage. And the first block is a charge amplifier. So that charge amplifier converts the charge into equivalent voltage. Then there will be some ADC, one ADC, and how much resolution we want, either 10-bit or the 12-bit resolution. And then the complete process will be, you can see, it is controlled by a microcontroller unit for our current work. And then the microcontroller unit, it will be connected through either USB or UART. So through which we can to retrieve the information, we can program the microcontroller, and we can set different parameters. So, so there are few microcontrollers are there from either analog devices or ST microelectronics. In our current work, we are using ST microelectronics microcontroller STM32, and there are some comparison of STM30. You can say STM based microcontrollers are there. So in our current work, what we are using in our current work, we are using STM32 F476 microcontroller, which has the 12-bit ADC resolution. It can be 12-bit. It has 1 MB flash memory within the microcontroller itself, so we can store the data, and it can be operated from 1.8 volt to 3.3 volts. And here we are using 3-volt battery, so it will be operated by using the 3-volt supply. So, so the charge amplifier will convert the charge to equivalent voltage. ADC will convert, which is we don't want to, we no need to use the ADC outside, because most of the microcontrollers nowadays, it has its own ADC. So the 12-bit ADC is there. So we use the.
Sir, please avoid so detailed, sir. Please go ahead.
Yeah, okay, sir. So these things we'll use, and then the memory, it has the internal memory. If it is sufficient, then we'll use the internal memory, or we'll basically interface some external memory with this microcontroller. So in our currently ongoing work, we have developed a customized STM32 based board by ourselves. So this is this one is one microcontroller. So the middle one, this IC, and we have made the custom board, and through this custom board, and this is the sensor connection you can see, and here you can see one piezo sensor. This is one piezo sensor from Chrysler 63 to 6312. So this is for the 1000 megapascal range. So this we have already developed. The testing is going on. This is the first prototype we have developed, and the similar kind of prototype also we want to develop for this proposal also, where for the blast pressure measurement, where the pressure range will be defined, and a different sensor can be, piezo sensor can be used. So there are 5 components: the sensor, signal conditioning unit, enclosure also that will be able to withstand the blast pressure, and a software package for the data storage and the retrieval, and the battery. So the major task, as I told you, the pressure sensor, we have gone through some survey, and we have seen that PCB piezoelectronics, we can have these models of the sensor we can use for this blast pressure measurement. So this is one typical specification of the sensor of 500 psi range. In the signal conditioning unit, the first block is the charge amplifier. The charge amplifier we want to build with the op-amp, which has the similar, you can say, the respective specification, the op-amp we have to set. Then we have the 12-bit ADC. The data will be 12-bit resolution. That will be, I think that will be sufficient, and we can go for the 1000 kilohertz sampling rate, or can be one mega samples per second also. That is possible, because this STM32 based microcontrollers, 80 megahertz, this signal frequency, its operating frequency is there. We can store the data. It can be 8K or 10K. I have said just one specific specification. We can store the data within the microcontroller, the non-volatile memory, and it will be a battery operated system. So then we have to design the enclosure, and we have to software package. We have to build the GUI through which we can program the electronics module. We can retrieve the data, and we can set the different parameters, and it will be a battery operated system. So we have to look for the carefully design the power consumption of the system, so that this battery will be this battery operated system will last long for whatever the data acquisition time is there. So this is the implementation details, whatever we will decide. So this is the typical pressure plot or the pressure curve you can see. So we have to measure the peak pressure, the duration, and this the negative phase may also be.
Please conclude.
So
please come to the last, sir. What is the duration and?
Sir, pardon, sir.
Sir, please come to the final. What is the duration and the cost for this approximate?
Yes. So this is the plan of the development. We want to make it. So these are the major milestones: signal conditioning module, then the multi-channel data acquisition system, then the field tire we have to make it. So for these two means the single module and the multi-channel, it can be of 3 or 4 years, because we want to develop the both of the systems. So that's why we make it 4 years. So if we have to develop only one, then it can be 2 or 3 years, you can say duration. It can be, once we develop the single module, then I think it won't take much time to make the complete data acquisition system. So these are the few works we have, PI and the groups we have done it before, like accelerometers, this you can say signal conditioning circuit, accelerometers. So these are the different modules at the hardware we have developed in our lab, and these are the typical publications we can have. These are the sponsored project we have handled. So currently we have one that ARMREP with the PXC collaboration with PXC Chandipur. We have the development of pressure measurement module for chamber pressure measurement we are currently doing. So these are the strength of myself and my co-PI Professor Kundu is there. And this estimated, we have given estimated, we want one to GRF or the SRF. So for the 4 years, we have made it around 80 lakhs. And within this 80 lakhs, we have the pressure sensors. The pressure sensors we have, you can say 4 pressure sensors. It cost, the pressure sensors are costly, this kind of. So, and also we want, so this is,
Sir,
yeah,
this is okay. Cost breakup is okay. I have 2 points, sir.
Sir,
You are already making a similar system for PXC. What is the difference between this and the proposed system?
Sir, for the PXC, it is the gun chamber measurement where the pressure range is very high. It is 1000 megapascal.
Sir, it does not, range is not a matter. Well, all sensor have some standard. They have the output of equal to some 5 volt, like most of the sensors, whatever we are using, the 5 volt output. IEP standard is there. So
Yes,
it may be 50 psi, it may be 1000 psi, it may be 1 lakh psi. It will always give a 5 volt voltage. So range is not a big issue here. So what is so special in there? Different between these two systems.
Sir, actually your voice is breaking, sir. Sir, the difference is there the requirement, the requirement is there the pressure profile that changes very fast within maybe you can say the 80 millisecond time is the most measurement, you can say the acquisition time. And their pressure range.
Sir, here we are interested in only 10 to 20 millisecond only. That is the only thing is that we need fast system. So, but I find that that sensor is only charge-based sensor, but mostly we are using the voltage mode sensor. IEP standard sensors are there. So this is you have to so you have to make a signal measure for that, and then the acquisition system. You have already shown that the PCB setup, how they are putting their gauges and they're recording the data, and you have already proposed a standalone system which can be combined with the sensor itself, so that there is no need of the cable. That is our requirement. In that requirement, I want to add only few things. First thing, we want more regulation. 12 bit is less regulation for us.
Yes, sir. Yes, sir. That would be fine if the 12-bit resolution is less.
Even the memory is less. I think when we are sampling at a very high sample, the memory depth you may require more. And then we want the system with both input as a voltage as well as this IEP.
Yes.
And second, more point is that when we are putting number of sensors in the field, we put the visual signal precision with the recorder with every sensor, how to synchronize all the sensors. Good.
Sir, if you want more resolution, then if it is the 12-bit instead of 12-bit, how much resolution you want, sir? 16-bit?
Minimum 18, sir.
Okay, so then we have to integrate one external, you can say ADC to acquire the data. We will not use the internal, whatever the, so that is one solution is there.
Sir, I suggest we have, when we publish this webinar, we have given some detail of the data system that we are requiring. You please check that also, so that you will get more input. So mostly we are using this PCB sensor with the not charge mode system. We are using IEP sensor which have the output as a millivolt per PSI range, like that.
Yes.
So whatever the PXC is using, that is charge mode sensor. We are not using mostly that sensor charge mode. We are using always IEP based sensor which have the output in millivolts.
Yeah, sir, this IEP sensor, ultimately that conditioning is there inside this IEP sensor. So that's why it is giving the voltage.
Sensor has inside its conditioning. So we need only power to that signal conditioner sensor.
Sir, those sensors have inbuilt electronics, but if we want to build the electronics itself, that can also be done, sir. Means purchase.
So please keep in mind our requirement is for that IEP type sensor, and with the minimum 1 mega samples and the resolution more than 18 bit, and the slightly large memory so that we can record our high sampling data.
Yeah.
And
Okay,
the
sir.
size is also very important.
Yes, sir. Yes, sir. Yes, sir. That will think, and maybe, sir, further
Otherwise, it's
discussion
very good.
maybe.
You have already experience with working such a sensor, and you are already making this system similar to that. Only this type of fine tuning will be required for our system.
Yes, sir. Yes, sir. Yes, sir. Yes, sir. That is true, sir.
Yeah. So my colleague Rajan also want to say something, please.
Yeah, I think if Inderpal, you agree, then we can invite him to TBRL to actually discuss the actual scenario. Okay.
That will be better.
Yeah, then we also require some memory in this
Yes,
multi-channel
then we
data
can discuss this and
larger
whatever the
memory,
requirement.
so that we can record the signals over there itself and retrieve through
In
optical
more
link.
detail. Sir, please.
We want that there must be a memory in the multi-channel data acquisition system also.
Yeah, you are mentioning memory, but that is very less. 10K is not sufficient for our application. So you have to increase the memory length. Yeah.
And then lastly, you have a good experience of designing all this electronics, and we will be looking forward that the time 3 to 4 years too long, so you can plan for 2 to 2.5 years at the most. Okay, so if you can shrink your timelines, then that will be appreciated. Okay, and then you can plan a visit to TBRL as soon as possible.
Interface one external.
Sorry?
Dr. Kaur, I suggest you go for a DTS company. DTS, they are already making slice nano and slice micro. We are interested in similar type of system. Hello? Dr. Sugata? I think link is broken. Are you able to hear us? I think, Rajman, it's good suggestion, proposal. We can go ahead.
Very good.
Both the proposals, the better the data system today we got, they are good. So we can go ahead.
We will go ahead, definitely.
Yes. Surely. Okay. Then we close this session and break for some time.
15 minutes.
After that, we will meet at 11:50 to start the next session.